The most important skills that you will need to have, especially in physics, is that you have to be able to resolve diagonal vectors into what we call x and y components. I think you might have been introduced to this in grade 11, if I'm not mistaken. So this lesson is titled Components of Vectors, and that is what I've just described is the first learning objective. So at least by the end of this video, you should be able to resolve diagonal vectors into x and y component. Remember, we said vectors are physical quantities that have both magnitude and direction. An example would be a force. A force is a vector. It has direction and magnitude. So a force of 10 newtons would be acting on an object maybe east. Momentum is a vector. Displacement is a vector. And then you also have to resolve force vectors on a slope. So remember, a slope is something like this. So you have to also be able to resolve those force vectors into parallel, what we call parallel and perpendicular components. It's not vectors here, it's perpendicular components. And then the second thing is that the third thing, actually number 3, is that you have to be able to perform calculations, at least for this lesson, involving diagonal vectors. In terms of parallel and perpendicular vectors, we will do it in another lesson. And then the other thing to keep watch for is that you should be able to define the term, the bearing of a vector as well as a resultant. We will provide those definitions and you need to be able to know those. So what is a diagonal vector? So sometimes you have a block maybe on a horizontal surface, and then you have a force acting on it. But this force is not either to the right or upwards. It's actually at a diagonal location. Let's call this force F. And then it actually makes this angle with the x-axis. Let's call that angle theta. So in calculations, you have to know the vertical. So remember, vertical is up, and the horizontal effect of the vector on the block. So how do we do that? To do that, we have to do something called resolving this force vector into its x and y component. So how do we do that? So let us redraw this entire situation. So we can draw this situation where we say this is my vector, and then I resolve it into its x component and perhaps its as well as its y component. And then if you look at this will form some sort of a square. So this side here, I'll say it's fx. So it's the x component of this force. This will be x component. And this one over here, I will call it fy. It's the y component, because it x component. How do you spell that? So it x in the y direction. But if you look carefully, let me just draw it not in with dashes. If you look carefully, we can, so this is fy, I forgot to put that there. This side here will be equal to this side if you assume this is a square. I know it doesn't look like a square on my drawing, but it is actually a square or a parallelogram. So meaning I can actually redraw this thing, this entire thing like this, and have fx here, and then put perhaps fy over here. It's unfortunate I don't know how to draw. So we have fy, fx, and f, and even then we have an angle there. And if you look at this actually makes a 90-degree angle with that, and this somewhat becomes a right angle triangle. So how do we then find the value of fy as well as the value of fx? To do that, we have to now borrow from maths a little bit and remember our trigonometric ratios. So those are, you can remember them by this thingy, soccer tower. So that would be the sine of an angle theta in a right angle triangle is given by opposite over adjacent. So this will be our no, I'm lying, it's not adjacent, my goodness. it's opposite over hypotenuse. So it's opposite over hypotenuse. And then the cos of theta is given by adjacent over hypotenuse. And the last thing we have is the tangent of theta is given by, or tan theta is given by opposite over adjacent. So this is what we call trigonometric ratios in mathematics. I'm just gonna wipe my board there at the top. So now if we have this and we look at our triangle, we see that, okay, this is my hypotenuse side, this is my hypotenuse, this side is opposite because it's opposite to this angle theta in relation to the angle, and then this side is adjacent. So adjacent means this side j, the next door of this angle theta there. So let us now expand. So we can say that sine theta in actual fact, so the opposite of this angle is fy, and then the hypotenuse we said it's f, right? And then for cos theta, I feel like I'm gonna run out of space. And for cos theta, let me remove this. And then for cos theta, we have that the adjacent angle we said is fx, the adjacent side, I apologize, and the hypotenuse side is f. And then for tan theta, we had said it's opposite over adjacent. And if you look, the opposite side here on this diagram to opposite to the angle theta is fy, and the adjacent side is fx. So now if you want to make fy the subject, it's a matter of just cross multiplying. So you can say it's cos over 1, cos theta over 1, or sine theta over 1. So you multiply 1 multiplied by fy and sine theta multiplied by f, and then you end up with that fy is actually f multiplied by the sine of theta, and we have now resolved this vector. So if you know the magnitude of f and you are given the angle, you can actually find the x component of that force. The same thing here, fx will be equals to f cos of theta. So if you have the angle and the magnitude, you can actually find the x component. Here normally we use this one when we're trying to find the angle or the direction. So you can just say theta. If I make theta subject of my formula, you know that becomes arctan, that is written like this, and then you have fy equals to fx. So those are just important things to take note of, especially when we talk about resolving something into its x and y component. So another interesting thing to note is that this vector here, this vector f, is actually called a resultant. Remember I said you need to know the definition of a resultant, and a resultant is defined as a single vector which has the same effect as the original vectors acting simultaneously on an object. So in actual fact, what is happening, let's say here, you remember your vector is acting on this object. So it's this x component and y component acting on this particular object, and then this f is just a single vector that combines the sum of these two. So we can actually go a step further and say, okay, what if you were given the x, the y, and the x component, and you have to find f? Since this is a right angle triangle, you now have to use Pythagoras Theorem. I'll show you now. So since this is a right angle triangle like we agreed, this means that if I want to find f and I'm given the x and y component, I can simply say use Pythagoras Theorem, which will say f squared, the magnitude of f actually, f squared equals to fx squared plus fy squared. So we are familiar with Pythagoras Theorem from math, and then to solve for f, I can just remove the square by introducing a square root on both sides. So we have fx squared plus fy squared, and then you will be able to find this value. But now let us actually do a calculation where we put all of this that we have learned into use. So let us say you're given a sketch such as that one. And they saying that that force, that applied force, acts on this object at an angle theta, at an angle theta, and that they say that the x component of that force applied is 50 newtons, and the y component is, no, the y component is 50 newtons, and the x component is 90 newtons, and they want you to find the resultant vector f and its direction. So that is our now we are now on lesson 10. So what we can then do is kind of redraw that situation like this, where we say this would be f, which is our hypotenuse, this would be fx, our x component, and our y component. And since it's a right angle triangle, we can use Pythagoras Theorem to find the value of f, as we've shown earlier. And then we want to be left on this side with f, so it's going to be fx squared plus fy squared. So there we are. So the value of fx is nothing but 90 all squared plus 50 all squared, and you can just put this in your calculator. I think it's going to give you a value of 102. You can check that the answer with me, 102 newtons. But we also asked to find the direction. In this case, to find the direction, we actually have to find the angle theta. So the angle theta, you said, is given by the arctan, which is fy over fx, and then we know that fy is 50 divided by 90. So you can also put this in your calculator, and I think you're gonna come across a value of 29.05 degrees. But now remember, this angle theta here is the angle, so it's the angle between the x-axis, it's this angle there, it's the angle between the x-axis to this thingy. But when we report these answers, when we report so let me just write this. So we found f to be 102.96 and theta to be 29.05 degrees. So I'm just gonna wipe this whole thing. And when we report these answers, so I want to draw a Cartesian plane, and I'll say this is north, south, and this is east, and that is west. And we would say maybe this is 0 degrees, and then we're going in the clockwise, anti-clockwise direction. This would be 90 degrees. How much is this? 180 and 270. This might be or 360 degrees. And then you see that that vector, that diagonal vector f, was actually here, and it made that angle. So from this from the x-axis to this angle, it was theta, which we found to be 29.05. But now when we report these answers, they actually want us to provide a bearing. So a bearing is a vector that is measured. So a bearing of a vector is measured from north to the vector. So a bearing will actually be from here to here. That is the angle that they are actually looking for, meaning to quote the final answer. So if this is 90, meaning 90 minus 29.05 degrees will actually give me the bearing that I want. So we'll just say, maybe let's call this angle, let's call it beta, not phi. Let's call it beta. So we say beta is actually 90 minus the angle theta. So 90 minus 29.05 degrees, and I'm not sure what value is it that you come with. Maybe it might be 60.95 degrees. And then to quote your final answer, you would say, therefore, the resultant force vector is equals to 109.96 Newton at the bearing of 60.95. I hope that is making sense, especially in terms of these bearings. So that bearing is measured from north in a clockwise direction to the vector that we're looking for. So if this vector was somewhere here, we would measure that bearing from north to this vector. Yep. So this brings us to the end of this lesson, and yes, I hope you enjoyed it.